Gaussian strip and data conjecture for K3 surface.
So maybe this is a good time to thank Michel and Katya for organizing this very nicely. It was a great pleasure to be here. Okay, yeah, so I want to talk about two things. I want to talk about the geometric results, which is Zarin's trick for K3 surfaces. So this is a completely geometric result valid over any field. Of course, I will explain what it is. And I want to, and I will give one application, which is the tape conjecture. For K3 surfaces. Okay, so maybe I should apologize because I talked about the proof of the tape conjecture for K3 surfaces in front of many people, but this is so this is not. I mean, this is a new proof, so this is not what is published here. And so maybe what I would like to emphasize. So I will give a proof of the tape conjecture. I will explain what the tape conjecture is, and give a proof for K3 surfaces over finite fields, and well, the feature that is probably a little bit better than before. But before I started to say, well, for K3 surfaces from finite fields, the only interesting case is Picard number 22, which for complex geometers is really not at all interesting. So this is a proof where you don't actually, I mean, of course you have to use it to your finite field, but you use it at a very small place. Okay, so I will talk about everything in the time or in the time. So so this will be something which is, I think, really very much related to everything that was talked about this week, especially, of course, K3 surfaces, algebraic cycles on K3 surfaces, and moduli spaces of sheaves of stable sheaves on K3 surfaces. So these will be the ingredients. Since we haven't seen any arithmetic geometry yet, I will spend maybe the first hour discussing what the tape conjecture is and how an essentially takes proof in 66 for Abelian varieties over finite field, and how Zarin's trick for Abelian varieties was the original version of Zarin's trick, and for the picture. Okay, so let's start with what the tape conjecture is. So we start with X, a smooth projective over K, and maybe K is any field with algebraic closure K bar. Let P be the characteristic of K, L is a prime number different from the characteristic. Okay, so we did a lot of complex geometry. In complex we use singular cohomology, which are the cohomology groups of X with coefficient in Z. Well, if the base field is not the field of complex numbers, but an arithmetic field, for instance, like this, then we have L-adic et al. Cohomology. So L-adic cohomology. These are groups. Hi of X. So this is a geometric thing. So you want to look at X over the algebraic closure of K with coefficients in ZX. Sometimes there are derivative. So for all intents and purposes in this talk, these are groups that behave exactly as in the complex case. They behave exactly as the singular cohomology groups. It just turns out that in characteristic P, you don't actually have cohomology group with Z coefficient by result of Z, so you have to put Z there. But these will behave as well as over the complex numbers. Okay, so we have these cohomology groups and we have a cycle class map. So from the Charles groups of X to et al. Cohomology, so again H2I as in the complex case, X over K bar, ZL. Okay, so exactly if we were doing Hodge theory, we would put a T2 is the power of 2I pi here. Well, there is a version of T2 in terms homology, so we have a cycle class, and so this conjecture is the following. So we look at so we assume that K, let's say, is a finite type over its prime. Well, I mean, not over, so it's finely generated as a field over its prime subfield. So it's finitely generated over its prime subfield. So which means that it is the function field of a variety either over Fp or over Q. Then, well, so let's look at this hyperclass map. So we have Chi of x mapping to H2i x over K bar. Okay, so we want to describe the image. So well, the first thing is that, of course, on the left-hand side we have a Z module. On the right-hand side we have a ZL module. So of course on the left-hand side I have to tend to by ZL. And since we know that the Hopf conjecture is not true for ZL coefficients, for Z coefficient, so we have a map like this, so two QL vector spaces, and well, let's notice one thing. So this is, so I told you that L-adic homology behaves a lot like single homology, but there is a very distinct feature, which is the following. So K here is really not algebraically closed. This is a hypothesis that K is really a small field in a way. So it has an absolute Galois group which acts on étale homology. So this is a very important feature of étale homology, of course.
What is the assumption? Sorry, in the.
I'm sorry. I'm sorry. Well, yeah, so F is finitely generated. So you know, it's just a function field over its terms, over a variety of its subfield. Anyway, so let's look at the topological case. Of course, the absolute Galois group of K bar over K acts on X K bar just by base changing by automorphism here. And of course, if we think about the topological situation, then it's highly discontinuous. The automorphism group of C doesn't act in a reasonable way on complex varieties. But here, its homology is only defined by finite covariance of varieties, and these pull back through automorphism of the base field. Through automorphism of K bar. So we have a Galois action of this very large group, complicated group. You know, well, if K is a finite field, this is just a Frobenius. If K is Q, this is a very complicated group. So we have a Galois action that and of course, the selective class map is Galois equivariant. So on the left-hand side, there is no Galois action. You notice that I didn't put the Charles group of X over K bar. I put the Charles group of X, so the variety over K over the non-algebraic closed field. And so the elements on the left-hand side have Galois invariant cycloclass maps. Okay? And Fick's conjecture states that this cycloclass map is. So in other words, the space of Galois invariants in L-adic étale homology is spanned by homology classes of algebraic cycles. Okay, so you have a lot of variations on this statement. So of course you could put you might want to put on the left hand side Chi of x over K bar, algebraic cycle that might be defined over a bigger field. But that doesn't change. That really doesn't change anything, because you have to realize that at the level of Charles groups, at the level of homology classes of algebraic cycles, the Galois action has to be very simple. So Charles groups, Charles groups they parameterize algebraic cycles. Algebraic cycles, they are parameterized themselves by the Hilbert scheme, and the Hilbert scheme of X is defined, well, is defined over K. Is defined over the ground field of X. So in the end, any cycle in xk bar, any algebraic cycle in xk bar is actually defined over a finite extension of K, so it has finite orbit. So I could have the exact same statement, putting instead xk bar on the left-hand side, considering algebraic cycles with coefficients in an arbitrary extension, even, well, either finite or even either transcendental or algebraic. And on the right hand side, I will just put elements with finite Galois orbits. So this is something about, of course, if you think in terms of Hodge theory, some transcendental part which corresponds to the part in analytic homology where the Galois action has infinite orbits. It's very complicated, and it's fine. Anyway, so of course, so I will recall what is known about this in a moment that you have to compare this with the Hodge conjecture. Okay, so the Hodge conjecture K equals C. So of course this is a very different situation because now, well, K is algebraically closed, and we still have a cycloclass map like this. So of course, as we know, it's safer to put rational coefficients, and this still maps to H2. Right? So we lost a little bit because now K is algebraically closed. We don't have any Galois action, but we again gain extra structure in the two following ways. So first, we have cohomology, similar cohomology has Z coefficient, so it's a much finer invariant. I'll come back to that. And well, here we have a Hodge structure.
One Q on the right hand side.
Oh, I'm sorry, yes. The right hand side is endowed with a Hodge structure of way too high, as you know, and so Hodge conjecture, the image is the space of Hodge classes. Okay, so this is a cohomological description of the classes of algebraic cycles. Okay, so I want to stress right away a very important difference between these two things, which is that the Hodge conjecture is way more precise than the Tate conjecture. The Tate conjecture, well, the Hodge conjecture, it tells you really that if you take a Hodge class on the right-hand side, well, there is a Q coefficient, so let's take some multiple. It will be the cohomology class of an algebraic cycle. So if you want to prove the Hodge conjecture, you start with a given Hodge class and you try to find an algebraic cycle up to a multiple. But here, you absolutely cannot do that because you have tensor with QL, which is much bigger than Q. So you can really not start with a cohomology class, with a Galois invariant cohomology class on the right-hand side and try to construct an algebraic cycle. Because in general, it will be just some linear combination with QL coefficients of different algebraic cycles. So strategically, this is not such a good situation. The Tate conjecture doesn't tell you the cohomology classes of algebraic cycles. It just tells you the QL span. So this is really different. Okay. So what is known? Okay. So for the Hodge conjecture, well, essentially there is there is one fundamental result, which is divisors. So let's check one more theorem. So that, of course, lots of you know, but I will recall the proof in a moment. This is with the modern technique. This is not too bad. So if I equals 1, so 2i equals 2, we know the cohomology classes of divisors in H2 of X. And actually, in that case, we can actually see that. So this is one thing that we know, and well, essentially, this is everything that is known about the Hodge conjecture in general. So of course, there are specific cases, but there are very few cases where it doesn't actually come from divisors, taking intersection, and so on. So this is one thing, and so for the Tate conjecture, well, the point is that very little is known. So we don't. So the thing that I want to stress is that we don't know the case of divisors. We don't even know the case of divisors. So Tate conjecture, we have essentially one result. So for K general, so as in there, we know divisors on abelian varieties. So this is the most important case that we know. So this was done in 2 steps. So in 66, there is a paper of Tate, which treats K equals FQ. and then in 83, so you see the two base cases for the Tate conjecture are finite field and a number field, and then you have function field of the T. So for the prime subfield, you get either FQ, this is taken 66, this is not too bad, I will recall the proof, and then in 83 you have the famous theorem of Faltings in the way of proving modest conjecture. Okay, so the number field. And then the function field case is due to the So I'm not putting a date because it does, I mean, it depends on which version of the function field case. So there is a series of papers of that. Of course, the function field case starts by applying the case of the characteristic. Okay, so this is what is known. So this is, I mean, of course, these are very important results, but this is a lot less than what is known about the Hodge conjecture. And then, well, once Tate proves the Tate conjecture for abelian varieties, for Weiss-Riemann abelian varieties, the next case is K3 surfaces. So for lots of reasons, for if you look at the classification of surfaces, if you look at the nature of the motive of the K3 surfaces, this is the next case. This is supposed to be the easiest case after abelian varieties. And so there has been a long story about this. There is, I think, in 73, there is a paper of Artin and Swinnerton Dyer for elliptic K3s over a finite field. Well, so that's one thing. In the 80s, so this is the only, I mean, this is right after, this is a few years after Tate, this is the only geometric result that they had. And in the 80s, so I think the final result is 83. There is
elliptic K3 or elliptic?
Oh, elliptic K3. No, very little is known outside of K3. So this is all K3. So in 83, with Nygaard and August, were able to apply a periodic Hodge theory to get the so-called non-supersingular or finite case. So this is, so I won't recall what it is because I mean this won't appear in the talk, but for K3 surfaces over finite fields, you have two cases which are of course are the same as for abelian varieties, where you have supersingular abelian varieties and finite abelian varieties. You have the K3 surfaces that look like their counterparts in characteristic 0, and then you have the so-called supersingular case. So they prove everything except the supersingular case. So that's one thing, and so things sort of stayed very calm for some time, and then, so in 2012, David Schmolnik had a very beautiful idea.
Sorry, I somehow missed. Who is supposed to be a finite case?
The K3. So this is the case of K3 surfaces. So in 83, Nygaard and August proved.
What is the K3 of finite case?
So I said, this will not appear in the proof, so I don't want to define. So it's like for abelian varieties, for instance, for elliptic curves, you have ordinary elliptic curves, the ones which have just a CM, and you have supersingular elliptic curves, which have quaternions for axiom. And so this distinction can be carried on to, well, first to abelian varieties, where you have the notion of height, and it can be carried on to K3 surfaces, where you have finite height and supersingular case. So they proved everything but the supersingular case. So the remaining case was the one that is supposed to be Picard number 22. Non-supersingular, yes. Anyway, yeah, this is not a distinction that will come up. So. Okay, so in 2012, Molnik and then myself, we gave a proof in characteristic P, I think, bigger, so at least 5. We had a proof, so this is a proof that directly treats only the supersingular case. This is really something like that. And in 2013, Kirtimada Pisipera proved, I think, for P, for odd characteristics. Okay, so
but it's proved now for supersingular than the iterations.
Yes, but that uses the Tate conjecture.
Ah, okay.
So yeah, of course. So I'm not. I mean.
Okay, no, just not.
Yeah, no, so this is a different part of the story. So Littke proved that supersingular is unidirectional, but he proves that what he proves is that pk number 22 implies unirational. So now everything is well, I don't think, yeah. Okay, so this is the situation until recently. So what I okay, and what I want to explain is that I want to, well, so let me just explain a little bit about this. So the key point, the approaches of Daleš Molik and myself and Martin Lepiga are very different, but they both rely very heavily on the arithmetic of the moduli space of K2 surfaces. So K2 surfaces, as you know, as for homomorphic symplectic varieties, they have a very beautiful moduli space, which is an orthogonal, which is open in an orthogonal Chinois variety. And well, these ones have integral models. They exist not only over C, but they exist, well, maybe not over Z, but at least over a large open subset of space Z. And what you want to do here is understand in a very precise manner the geometry of this moduli space and of its special subvarieties in characteristic P. So this is why restriction on P appear, because you want to be able to do periodic Hot theory to study the geometry loci, essentially. And the other feature of this proof is that it relies very heavily, the two proofs there rely on the so-called Puga-Zapata construction. Again, I will be very brief about this because the point is not to use it today, but so the Puga-Zapata construction is the following. So it's due to Puga-Zapata and the link we used it to prove the Bell conjecture for K2 surfaces. It tells you that if X is a K3, then H2 of X, so purposely I'm not writing any coefficients here, so you can really choose your favorite cohomology theory. It is naturally a sub-Hot structure of the endomorphism of H1 of A for X. So X is a K3, A is Puga-Zapata abelian variety. So there is a construction of an abelian variety associated to any K3 surface, which is very mysterious. So it's really a transcendental construction. You don't construct an abelian variety per se. You actually construct a torus through hot theoretic data on H2, and then it turns out that this torus is an abelian variety and fits this. So these approaches to the technique of K3 surfaces heavily rely on this. And the strategy is actually very simple. If you have a very clear way of approaching this, you start with a cohomology class on X, which is Galois invariant, and then you want to prove that it's a divisor. So let's assume that we are in characteristic 0, and I will give you a very short proof. So we start with a cohomology class, which is Galois invariant there. So we have an embedding like this, which is canonical, so it's Galois equivariant. So we get a cohomology class on the endomorphism of H1 of A, which is also Galois invariant. And by Falting's theorem, or so by Falting's theorem in characteristic 0, this is the class of an endomorphism of A, right? But of course, I mean, we don't really know the relationship between A and X, so we cannot go back. But if it's a class of an endomorphism, then it's a Hodge class. If it's a Hodge class, then since this is a morphism of Hodge structures, because it's, as I said, it's canonical, it exists for all cohomology theories, it means that the class you started with was actually a Hodge class. And since we know the Hodge conjecture for divisors on X, we are back on our feet. Okay, so this is a very weird process of going one way and another. And it only works in characteristic 0 well because I use Hodge theory, and also because for a different reason, is that, you know, I told you that I had this, that you couldn't start to prove the Tate conjecture by picking a class and expressing as a divisor because of the QL thing, right? But in characteristic 0, you can start a little bit like that because you have the Q rational lattice, well, the Q structure inside H2 of X given by singular cohomology, which you can absolutely not do in characteristic P. So in characteristic P, you start with this, and then, well, then these are, and then you can prove that. Okay, so the goal well, maybe make mistakes. The theorem, so the theorem that I want to explain today is the Tate conjecture of, let's say, for K2 surfaces of finite fields. So theorem, the Tate conjecture holds for K3 over finite fields. Okay, so this is the theorem. So it's slightly stronger because we get characteristic 2, so it's always nice, I mean, at least to have a not known theorem, but this is the case of characteristic 2 is really not the motivation, and you don't see it in the proof. So the feature of the proof that I really want to emphasize is that there is no Kugler-Stagger constructions. We never see an abelian variety. You really work on with a given K3 surface directly, and there is no periodic Hodge theory. Okay, so this is a geometric proof. Okay. So maybe I should say, the Tate conjecture is a little bit more general than this, so because you allow function fields as well, and it's not so hard using Kugler-Stagger now to extend, once you have this statement, to extend it to function fields. So of course, so the main, I mean, the techniques that I will explain, in principle, they should work for function fields. The bad thing that as soon as you start with K-fields or function fields, you need semi-stable reduction to do anything, and we don't know that in this practice. Okay. So this is what I will explain, and to explain the strategy of this proof, I want to go back, and that's what we do before the break, to Tate's proof, and Zion's take for abelian varieties and Tate's proof of the Tate conjecture for abelian varieties of finite fields. So let's make just a very basic thing that not of you know. So recall the proof of the Lefschetz-Wahlmann theorem. Okay, so you start with X over C, a smooth projective variety, and you want to understand the chronological classes of divisors. So the way you do that, the easiest way to do that is to use the exponential exact sequence. So you have Z, the constant sheaf Z, mapping to the constant sheaf OX, the sheaf of all functions OX, and then here notification to pi, and OX, you have the exponential map, mapping to OX star, the sheaf of the irreducible homomorphic function. Okay, so you have an exact sequence like this because, well, locally you always have a logarithm. Okay, and this gives you the long exact sequence, give you what? So we start with H1, X or X star, so this is peak of X. Mapping to, well, to exactly what we want, H2 of XZ, and this is really the first strong class map. And this map to H2 XOX. So it seems like we're really good in the sense that, well, we know exactly what the image of peak X in H2 of XZ is, because it's the kernel of this map, which is the kernel of Hodge classes. But the key point is the following. So this is very good, but I was a little bit imprecise here, because while X itself is an algebraic variety, this exact sequence is not an exact sequence of sheaves on X as an algebraic variety, because I have the exponential map. So this is not an exact sequence of sheaves of the high-speed topology, this is an exact sequence of sheaves on X as an analytic variety, as a complex manifold, and that was the usual topology. So here, I have H1 of X or X star, but for X as an analytic variety. So this is not the group of line bundles, this is a group of analytic line bundles, right? And so the key point is that peak X is actually the same as peak X analytic. So any analytic line bundle is actually has an algebraic structure, comes from the line bundle of the algebraic variety. This is B2 and this is Gaga. And so in turn, if you want to express this in terms of curves, this is a way of saying that any analytic line bundle actually has an homomorphic section, which is not a trivial fact on a projective variety. And so let me just say one thing, and this will come up very soon for Tate conjecture. We have two steps, even in the proof of the Lefschetz-Wahlmann theorem. We have a somewhat formal step of applying the exponential exact sequence. This is a machinery that gives us control over the first strong class map. So this will exist again in analytic topology, this is the Kummer exact sequence. But then we have a highly non-trivial step, which we are very used to because this is a rather old theorem step, but which is some kind of algebraization result, some kind of convergence result, actually. So if you analyze, for instance, the proof of Gaga, this part, the fact that any line bundle actually has, or any coherent sheaf on an analytic coherent sheaf on an algebraic variety is actually algebraic, this is not a construction result, it's a finiteness result. The key part of Serre's proof, so you have, of course, a general homological machinery, but the key part is a cohomologic group of analytic coherent sheaves are finite dimensional, which is, I mean, however you phrase it, is not a formal result, it's not given by a big machinery, you have actually to prove some kind of finiteness for, for some differential operators and so on. So this, in the end, even the Hodge conjecture for divisors, is the crucial part is a convergence result. So you have some kind of analytic data and you want to say that power series that define this converge. Okay, so the same thing actually applies in the setting of the Tate conjecture. And it's the following. So Tate conjecture, we can start in the same way. So of course we don't have the exponential exact sequence, but we have the Kummer exact sequence. The Kummer exact sequence, this is the following thing. So we have mu L to the n. This is a sheaf of L to the nth root of unity on X. So this lives inside Gn. So Gn is the same as OX star, if you wish, the sheaf of invertible functions, and this is the kernel of multiplication of power L to the n. Right? So we have a Kummer exact sequence like this, and it gives you, well, what does it give you? If you look at the long exact sequence, you have h1 of x with coefficient gm, which is peak of x. So you have peak of x mod L to the n, mapping to h2 of x mu L to the n, mapping to what? Mapping to the L to the n torsion of h2 of x gm. So this is the L to the n torsion of the power. Okay, so this is formal. We don't have anything to prove here. And so let's just look at it a little bit. So let's not discuss the fact that I was looking at cohomology with of x over k bar, or x itself. So here it's really x over the ground field, so let's not worry about that. But this exact sequence tells you the image of peak x inside h2 of x mu L to the n. And look here, so that's what I just said. I'm looking at the cohomology of x, not of x over k bar. So this is directly almost the same as taking the Galois invariance here. So this is directly Galois invariance here. You don't have k bar. So you want this map to be surjective, essentially up to a finite index. So this means that you want, okay, so you want this group to be finite. So the Tate conjecture is equivalent. It's not a matter of constraining divisor. It's equivalent to a finiteness result. And that's why I wanted to compare with the Hodge conjecture for divisors. So corollary, Tate for divisors is the same as the fact that the power group of x, and then I look at the L primary torsion part, and this is finite.
Is it for any source or for any event?
Yeah. Yes, overall smooth project.
So this is just equivalent. Yeah?
Yes, this is just equivalent. Yeah, no, there is not, I mean, this is completely formal. So, okay, so you need to do something like that. So let's step back and see what this means. So this is actually a geometric result, right? Because we are not looking at some, very weird cohomology group. This is a power group of x. If you know something about the geometry of x, so of course we can assume that x is a surface. If you know something about the geometry of x, then you can interpret in a geometric way the power group of x, right? So for instance, if you start with a pencil of elliptic curves on the varieties and the power group of x, the element on the power group of x will correspond to torsors under the Jacobian fibration. So this is something about the finiteness of actually geometric objects. So I will come back to that in the K3 case. But I think this is a good time to unwind everything and explain what happens for abelian varieties. So this is a very simple, I mean, the finiteness result is very simple to express. Okay, so this is Higgs proof of quantitative conjecture for divisors on abelian variety. This is slightly, there is some slight anachronism here because Darwin's paper counts up just a few, just a little bit of things, so it signifies the proof. So here's the thing. Let me just not even use that, but express the finiteness, a finiteness criterion to prove the Tate conjecture. So okay, so reduce to the following statement. So of course, the Tate conjecture a priori talks about divisors on the single abelian varieties, but of course, this is the same as talking about morphism between two abelian varieties, right? As you know. Using the dual abelian variety, so if you want to characterize morphism between abelian varieties by morphism between their H1, this is taking product, you just have to characterize projectors of abelian varieties. So you reduce to the following. So A, an abelian variety, over K, finite. And then let's take W inside H1 of A, let's say ZL, okay? I'm sorry, so this is geometric thing, So this is a very simple, this homological is very simple to express. This is a Tate module of, to a dual, this is a Tate module of A, so this is the direct, the inverse limit of the L to the n torsion points of A. Okay, so this has dimension 2G, and this has a Galois action, which comes from the Galois action on the torsion points of the variety. So you take a W inside H1, which is a Galois invariant ZL submodule, and you want to show that W comes from the direct. Well, up to, there is some isogeny that might be involved, but it comes from a direct factor of A. So that's the general yoga of H1 and H2 and abelian varieties, divisor and morphisms gives you this. Okay, so here is how you do this. So let's define maybe Sn. So apparently it's not easy to construct an abelian variety like this directly, but what we can do is control a subgroup of finite index on H1. So generally we cannot do that, but let's cook up a subgroup of finite index of H1 starting from W. So let's start with W plus L to the n H1 Z. Okay, so this is a subgroup. This is a sequence of approximations of W's as when n grows. But all of these are finite index because they contain L to the n H1. So we find let's say Dn, an abelian variety, such that Dn actually maps by an isogeny to A and let's say Fn north star H1 of Dn over Q bar ZL is Xn. So if we have a subgroup of H1 of finite index, we can always find an abelian variety with this precise mapping to A with this precise H1. Okay, this is just because, well, if you take duals, it means that if you have a Galois invariant subgroup of torsion, you can just take quotients by this subgroup and you get another abelian variety, which is isogenous, right? So this is very basic. And well, here we're sort of stuck because what should we do? So Xn as n grows to infinity is a sequence of approximation of W. So we want to pass to the limit. But of course we cannot pass to the limit on Vn, this is just a sequence of random abelian varieties. But the fact is, if there exists a B an abelian varieties such that the Ni, well, the N is isomorphic to B for infinitely many B's, then I'm sorry, what? I'm sorry. Then we are done. Okay, so this is what it does. Well, what happens if there is infinity many, if one given abelian variety appears infinity many times in this sequence, then we can actually pass to the limit, because we don't have to pass to the limit on B, we just have to pass to the limit on the Fn's. And so that's why, taking dual Fn and playing with the dual, you actually get an abelian variety with an endomorphism that has to be a projector on Xn. So you can pass to the limit here. Okay, so you pass to the limit, you get an endomorphism, of course, tensored with ZL. That's
so in a sense, it allows you to renormalize it.
Yes, exactly. That's the way you should see it. So okay, so in the end, as I said before, with the general argument about the power group, the take conjecture is equivalent. I mean, well, it would be equivalent, but it is implied at least by a finite statement. The only finite statement that you need is the following, so a very crude finite statement, which amazingly turns out to be true. So we only need to show that you fix G, then there exists only finitely many isomorphism classes of abelian varieties of dimension G over K. Okay, so if you start thinking about this, is a very weak statement. So what is clear? So abelian varieties come with the polarization, and the polarization has some degree. So for instance, if the degree is 1, you have principally polarized abelian varieties, and otherwise, you know, it's a little bit more complicated. And what we certainly know is that if we fix the degree, the space of abelian varieties with a polarization of fixed degree is given by a limited family. Actually, we have a nice modular space of abelian varieties with polarization of fixed degree. So for fixed degree, I claim that this is okay. And why is that? Well, once we have a limited family, the set of abelian varieties, let's say of principally polarized abelian varieties of dimension G over K, this corresponds to points with value in K of a nice modular space. But any variety of finite type over K only has finitely many K points if K is a finite field. That's just a big thing. So if the degree is fixed, then for completely basic reasons, we have only finitely many abelian varieties of fixed degree. So this is the same thing as if I look at quartic surfaces in P3, so K3 surfaces of degree 4, then of course we have only finitely many of those, because you just such a variety is given by an equation, a degree 4 equation, 4 variables with coefficient K, and well, we only have finitely many of these if K is finite. So what is of course much trickier is that a priori we have infinitely many possible degrees. So we have finitely many abelian varieties in each possible degree, but then the degree might be arbitrarily big. So in the end, this finite result is the same as claiming that abelian varieties over K always have a polarization of low degree, which is certainly not true. Which is certainly not true over C, because you have abelian varieties over arbitrary. And this is where Zimmer's trick comes up, which is very surprising. So we take A over K, so this is a different case. This is arbitrary abelian variety over arbitrary field. Well then, of course, A itself might not be principally polarized, but A cross A dual to the 4 is principally polarized. Okay, so this is really surprising. I'm not going to prove it, but this is not a really difficult thing. So the 4 is always, I mean, it's always a bit tricky. So first, of course, with the A cross A dual, so one good thing is that this stability variety is clearly isomorphic to its dual. So that's first, that's a good check. The 4 it comes from the quaternion trick. So you have a degree of polarization here, and you express the degree as sum of 4 squares, and then you play a little bit, and you actually find a polarization. So this is not a, I mean, this is a geometric statement, but the proof is absolutely not geometric. We know how to construct polarizations on varieties, on products, and so on. It's very easy. It's controlled completely cohomologically. And so what happens essentially is that as you take products, large products, the Néron-Sedley group of the abelian varieties goes bigger and bigger, and you have more room to actually find polarization. You have a lot more line bundles coming from the polarization of A, and the pullback, and then it just turns out that you have enough room to find a principal polarization. And then you're done. So let's just finish the proof, and then maybe this will be time to take a break. Start now over a finite field. As A varies over all possible abelian varieties over K, A cross A dual to the 4th can only take finitely many values because it's a principally polarized abelian variety. So I told you, if the degree is fixed here, the dimension is obviously fixed. So this one takes only a finitely number of values. And then you apply another easy result, so to conclude, which is also valid over an arbitrary field. So here is what you want to add. An abelian variety has only finitely many direct factors up to isomorphism. Okay, so this is not so difficult lemma of the endomorphism ring of an abelian variety, and then there are only finitely many projectors in the endomorphism ring up to interior automorphisms. So here is, so now that you know that A cross A dual to the 4th can take only finitely many values, for a given B, you have only finitely many ways of expressing it as A cross A dual to the 4th. And so you're done. And so this proves the result here, and by the construction of states that I explained before, this proves the state conjecture from any varieties. Okay, so this is the end for the introduction. Let me explain just before the break what I will do after that. So as I told you, part of this argument, there are two, so part of this strategy is something very general. The state conjecture over for divisors on an arbitrary surface of a finite field is equivalent to a finiteness result. It's finiteness of L torsion, L prime torsion in the power group. So this is completely general. Now, in a lot of situations, and especially in the case of K2 surfaces, this can be translated into a finiteness result like this. So I will explain, so this had been proved by Molick, Snowden, and Lieblich, Molick, and Snowden, and I will explain slight variation on this. The state conjecture for K2 surfaces of a finite field is equivalent to the fact that there exists only finitely many K2 surfaces of a finite field, which has the same problem that if I fix the degree as I explained, of course there are only finitely many K3s of fixed degree over a given finite field for a moduli space reason, but the degree might go up to infinity. So another way to say this is that, well, if I give you a K3 surface over K, over finite field K, you always have a polarization of low degree, which only depends on K. K is fine. So that's what I will recall, exactly how it goes, and I will explain that. And so we need a Zarin strip. So I have no way of actually constructing a low degree polarization directly, but what we will do is replace that in strip by the only natural thing that you can do. So of course, if you start with a K2 surface, you're not going to take products of X. That's a very bad operation, right? But as we saw this week, the natural operation is not to take products, it's to take Hilbert scheme. And maybe not to take Hilbert scheme, but to take modular space of stable sheaves. And we control that very well. We know a lot about the geometry of these. And so what I will explain is that if you take a family of K3s of unbounded degree, then you can, for each of them, you can find one modular space that lives in a bounded family. So this is not, I mean, we don't have principal polarization, but we can find unbounded family of K3s and bounded modular spaces of K3s with infinitely many components that all map almost injectively to a single modular space of homomorphic symplectic variety. And this is that. And I think this is what should be called Zarin strip for K2 surfaces. And so I will explain that and how you actually prove the take conjecture for K2 surfaces over finite field. So most of the talk after the break will be actually over an arbitrary field and completed geometry. So the only place where you use a finite field is just that variety or finite type over finite field also only has finite linear blocks. Okay, so.
So we can take your
25?
You agree?
Oh, yeah, yeah, no.
Just try to facilitate.
You heard that already. I need to hide it. I think it's not actually.
Я не смогла оставить
Мой муж,
Это будет хороший, но он не связан, да.
у нас